Okay, so we're going to start by talking about an age distribution. This is an example from your textbook. There's a table here that tells you the distribution of ages in the US in 1995. So age 0 to 20 was 29% of the US population in 1995. 20 to 40 was 31%, 40 to 60, 24%, etc. Okay. So when you add up these percentages, what do you get? 100% of the population. Yeah. So we just have transferred this information from the table to a histogram. Okay, so each of these rectangles, the area of each of these rectangles tells you the percent of the population who's between the ages at the bottom, 0 to 20, 20 to 40, etc. All right, so using our histogram, what percentage of the population is between 20 and 60 years old? 55. Yeah, we just add up the percent that's between 20 and 40 and the percent that's between 40 and 60. So we get 55%. All right, how about between 75 and 80? Yeah, a quarter of 13. So that's sort of the best we can do because they're only giving us information in 10-year intervals. So if that's broken into four intervals of 5 years, so you start at 60, then you go 65, 70, 75, 80. So we're interested in what percentage is in that 1/4 of the age bracket. So we would say, well, maybe it's 1/4 of the percentage. So we'll say 13/4%. And that's got to be an approximation, right? This one was perfect because it was in intervals of 10. All right, how about between 80 and 85 years old? Three divided by 4, 0.75%. So we're just going to do the same little game here. We're looking at this first quarter of the age bracket between 80 and 100. So maybe it's a quarter of that percentage, 0.75%. All right, so we want to identify whether each estimate was an over or underestimate or can't be determined. So this one was perfect, right? Because we had all the information we needed to answer that. But between 75 and 80, do you think that in this age bracket between 60 and 80, do you think there are more people towards the 60 end or more people towards the 80 end? Probably more towards 60 because 80 is like pretty old, right? People start to die. So this 13/4% is probably an overestimate. It's probably too big. There's probably more people down at this end than up at this end. And how about my 80 to 85 estimate? Is that too small or too big? It's probably too small because it's at the lower end of the 80 to 100 range. So there's probably more people down here than there are up here. So this is probably too small. Yes. No, what we could figure out from this is the average age of the US population. Yeah. Okay, so to be able to more accurately answer those questions where we had an overestimate and an underestimate, we would need to refine our histogram to have thinner rectangles. They would have to give me more information. And instead of 20-year intervals, we're doing 10-year intervals now. And I've broken the percentages down by 10 years. And then if I wanted to be even more accurate, I could do 5 years and then 1 year and then 1 day, right? And I would have these teeny, 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 tiny rectangles. And when I smooth it all out, I get this blue curve. Just keep thinning out the rectangles, figuring out what percentage of the population is exactly, 12 years and 1 day old. and that tiny rectangle would represent that percentage. So a density function is basically a smoothed out histogram. So the formal definition of a function p of x, it's a probability density function, or PDF for short, if all of the following hold. The fraction of the population for which x is between a and b is equal to the area under the graph of p between a and b, which is an integral. Okay, so if we're talking about the fraction of the population for which x is between a and b, the fraction of the population whose age is between some a and some b. Okay, if you're going to go from negative infinity to infinity, the fraction of the population whose age lies between negative infinity and infinity is what? Everyone. So for a PDF function, the integral from negative infinity to infinity of p of x dx is always 1. You're always representing the entire population as the area under the curve. And p of x always has to be positive, because we're talking about the percent of the population that satisfies some requirement has to be positive, has to be a positive fraction. Smallest it can be is, well, 0% of the population satisfies that. Okay, so this is what makes a PDF, is that the area under its curve is 1, and it's always positive. Okay, so I've given you a PDF, which means we know that the area under the curve is 1, and we want to calculate C. Okay, so the area under the curve is 1/2 times 4 times C, and that has to be 1 to make this a PDF. So we solve for C, and you get 1/2. Okay, another kind of density function that is related to the PDF is a CDF. A CDF is a cumulative density function. It accumulates the probabilities from the PDF. And there's the notation can be confusing. Your book chose this notation, so I'm following it. It uses capital P for the cumulative density function and little p for the probability density function. Big P for CDF, little p for PDF. So you have to be careful which one you're writing, big P or little p. So the definition of the cumulative density function is just the integral from negative infinity to t. So capital P of t is the integral from negative infinity to t of p of x dx. That means the area under the PDF from negative infinity to whatever input you're given. Or the fraction of the population having values of x below t. If we're talking age, it would be the fraction of the population that's below some given age. So instead of breaking it down from 10 to 20, I'd be asking the fraction that's between 0 and 20, less than 20. Okay, so I've given you a PDF. We know it's a PDF because the area under the curve is 1. It's always positive. Or they told me it was a PDF, which means that its area under the curve is 1. I want to sketch its CDF, the cumulative density function, but first I need to know the value of C. So we're going to do the same thing we did earlier to try to find the value of C. So I'm going to break this into 2 rectangles. This first one, its area is 1/2 is the base, and the height is 2C. And then add the area in the next one. Its base is 1/2 and its height is C, and that has to equal 1. The area under the curve has to be 1 for it to be a PDF. And then when you solve for C, you get 4/3. So to sketch the CDF, cumulative density function. So we're accumulating the area under the PDF. So I'm going to draw a little, this is X. So let's see, I'm going to put on 0.5 and 1. Okay, so let's think about this in terms of age. We're going to have this be age 0, this be age 1. So maybe this is like an infant daycare. Okay. And we're talking about the percentage of the population whose age is less than a half. Okay. So the percentage of the population whose age is less than 0.5 is the area of this rectangle. What's the area of that rectangle? C, which is 4/3. Well, it's not, it's 1/2 times 4/3, which is 2/3. Yeah. So let's put some units on here. This is 1/3, 2/3, 3/3. Okay. So the area of this shaded blue rectangle is 1/2 times 4/3, which is 2/3. So the percentage of the population that has an age of 1/2 or less is 2/3. The percentage of the population that has an age of 1 or less is 3/3. Yeah, it's the entire area. The percentage of the population that has an age of 1 or less, that is 1. Okay. What is the percentage of the population that has an age of 0 or less? 0. So at 0, 0, 0. So when I connect these, and then what is the percentage of the population that has an age of, say, 2 or less? Still 1, yeah. So this continues like that. And this actually continues to the left. This is always 0. The percentage of the population that has an age of -2 or less is 0. Nobody satisfies that requirement. Nobody is -2. So this is my CDF graph. It is the cumulative density function, or the accumulation of area under the PDF. Okay, so some observations we can make about CDFs from this picture. What is the limit as t goes to infinity of this CDF? 1. That is always true about a cumulative density function. Because eventually, everybody satisfies, everybody's between the age requirements, right? All right, what is the limit as t goes to negative infinity of p of t dt? 0. And p is monotone. That means always increasing or always decreasing. So p is monotone, which one? Increasing or decreasing? Increasing, always going up, because you're always adding to the area. So it's always going to be increasing. Okay, and then for p prime, we have to remind ourselves about the fundamental theorem of calculus part 2, the weird one that we don't use very often. So if I want to take d dt of this, the definition of p of t, do d dt of the integral from -infinity to t of p of x dx. So the fundamental theorem of calculus part 2 said for any number up to t, when you take the derivative, it's just the function, but you change the name of the variable. So this is p of t is the derivative. So the derivative of big P is little p. That's why they're named big P and little p, because one is actually the derivative of the other. That's a little lowercase p, lowercase p. A lot of distributions turn out to be normal distributions, better known as a bell curve. So a normal distribution has a probability density function, or PDF, of this crazy thing, where mu is the mean of the distribution and sigma is the standard deviation. So things like average height of American men, right, could be expressed under a normal distribution. So the normal distribution looks like a bell curve. So it's something like this. And the area underneath is 1. And the area over here is really small. That means that the percentage of American men who are like 7 feet and taller is very small. And then over here might be like 3 feet and shorter, very small percentage. And then the largest percentage is here in the middle, I don't know, somewhere around like 5'9", something like that. So all normal distributions are just transformations of a standard normal distribution. Mean is 0, standard deviation is 1. And there are tables and tables of these things that you will study if you ever take a statistics class. Okay, before we move on to the activities, I just want to make a note. When you take the test on Wednesday, you're going to be expected to demonstrate an understanding of how to use slicing to build an integral for problems that involve finding area or volume or mass or work, and for present and future value of money. Draw a slice, sum up the slices, transform that into an integral. But that is not the expectation for probability. You're free to just apply some magical formulas that you'll discover in the activities. All right, you can go ahead and start.